In order to understand beyond just motional EMF, we need to introduce a new concept called magnetic flux. Now, we've already talked about flux before in an earlier chapter, and we talked about electric flux. So we're just going to extend this concept to magnetic flux in this case. And so that's going to be our next step. This is actually how your book starts, chapter 30, just introducing flux. It didn't explain why it introduces flux, though. And so I'll try to do that. If you remember electric flux, we thought about electric flux when we talked about a charge, and we started looking at the electric field, and we said, well, how much electric field goes through a surface? And so we came up with this concept of electric flux, okay, and we said the electric flux was the integral of E dot dA over the surface. So we're going to do the same thing with magnetic flux. Magnetic flux is going to be integral B dot dA through a surface. So if we have a surface here, magnetic flux will be the total magnetic field through that surface. Okay, so if, for example, we had a circle right there, okay, and the circle was, radius r, and the magnetic flux was going through there, the magnetic flux, because it's going straight through there, same thing, dA is going to be a vector in the direction that's orthogonal to the surface. So in this case, the integral, if it's going straight perpendicular to the circle, integral is just going to be b times a. Okay, so the magnetic flux here is going to be b times a, or in other words, it's going to be b times pi r squared. Okay, so if your magnetic field is going through a circle that's like that, and it's tilted some angle theta with respect to the magnetic field, so in other words, the perpendicular to the circle is tilted, then in that case, the integral B dot dA, this is going to be exactly like we did for the electric flux. So this is going to be B times A times the cosine of the angle that's between the perpendicular to the area and the magnetic field. So that would give you B pi r squared times cosine theta. So this gives rise to the idea of magnetic flux. Okay, so how do we use that? Well, let's consider a case in which we have a magnetic field into the board, or into the page here, into the screen. So now we have this magnetic field that's into the screen, and I've got a moving object right here. Okay, and it's sliding along these rails, okay, connected to a resistor right here. Okay, so it's sliding along the rails, some velocity v. The rails are some length L apart. Resistor is some resistance R. Okay, magnetic field B. And so what we know is, for this particular configuration, there's going to be an EMF in there. And the EMF is going to be voltage, that's our EMF. And that's going to be equal to VBL. Little v is the velocity. Okay. The direction of it. Right-hand rule. Put your hand in the direction of v, the velocity. Curl your fingers in the direction of the magnetic field. and your thumb is going to point upwards in this case. So that's going to say this is the positive end, this is the negative end right there of our EMF. So that would suggest that current would flow this way through the resistor. So it goes from plus to minus. And so that means that current would have to be forced this way in here. Well, now you actually start seeing why we call this EMF, because now you're actually forcing the electrons, you're forcing them to go upwards, you're forcing them to go downwards, which means current, remember current goes opposite the electrons, current is going upwards in that conductor that's moving right there. So you actually are having electric force. It's motive because you're moving, that's making the electric force. And then you've got that produces the voltage. So this is a true EMF, and so that's where the term actually came from. And so now we see that the voltage in this configuration is going to be given by VBL. Okay, and so, well, how does that have anything to do with flux? Okay, so let's draw this somewhat smaller right here. So we have here this thing moving some velocity v. That's some L right here. Okay. And we say, what would be the flux through that circuit in here? In other words, in this enclosed circuit right here, what is the flux? Well, we know the magnetic flux is the integral B dot dA. Okay. So that's good. In this case, that's going to be equal just to B times A. Well, what is A? Well, A is going to be this horizontal distance right here. I'm going to call that X. And the vertical height Y, well, the vertical height Y is just L. So this is going to be B times X times L. Well, what's the EMF in here? The EMF, V, equals VBL. Okay, so this is big V for voltage, little v down here for velocity. So the voltage is VBL. Well, what's the relationship between the two? Well, the B is the same in both of these. L is the same. So what's the relationship between X and L? Well, velocity is dx dt. Well, area doesn't change. Magnetic field's not changing. So that means we could then say if the flux changes, so area would be changing. Actually, area is changing because X is changing right here. So we could say that the magnetic flux, the derivative of the magnetic flux, is going to be VBL. Okay. So that is going to be the EMF. Okay. And so that is going to be the voltage right here. Now, you're starting to notice there's confusion here in some of these equations. It's getting complicated keeping velocity from voltage because we got too many V's. So what we're going to do now on is for EMF, we're going to use kind of a script E. So that's going to represent EMF, and so that's going to be what we had been using as the voltage. So that means we can then say that the EMF in motional EMF is VBL. So that's our motional EMF. Well, notice that that's also the EMF in that circuit that we just had. Okay, so that is going to be the EMF in the circuit as well. Okay, well, your book writes this as minus VBL. Now, what's the minus all about? Well, in a little circuit, magnetic field into the board, if I move this thing to the right, that makes the top positive, the bottom negative, and current flows counterclockwise. If, on the other hand, I were to make it move to the left, then what would happen is that would make the bottom positive, and so current would flow clockwise. So the direction of the current depends on the motion right there. Okay, well, notice as the thing's moving to the right, the area is getting bigger, so the flux, which is B times A, is getting bigger. And so that means that an increase in area makes it go one way, a decrease in area makes it go the other way. So this is increasing. So this up here is increasing flux, that's decreasing flux. Well, if the current is flowing this way, right-hand rule points to a magnetic field out of the board. If the current's flowing this way, right-hand rule points to a magnetic field into the board. What that's saying is that this encourages a magnetic field, induced magnetic field, to be in the direction that minimizes change. And that is what we call Lenz's law. Okay. So I'm almost out of time that I can post for this particular video, so I will follow up with part 2.